Okay, we're going to talk about exponential functions and equations. Any function that can be written as y equals a times b to the x, where a and b are just constants. A couple of restrictions on these things. B, of course, are constants, and b will be positive and yet not equal to 1. So b could be a decimal like 0.3, it could be 1.7, but it's not going to be 1 because it's not going to grow or decay if you keep multiplying 1 by itself. Not terribly important that you have those things memorized or anything like that, but just recognizing that that's the nature of an exponential function. Probably the most famous template for an exponential function is one that's used for financial growth, usually, and that's the amount of money that you might have if money is being compounded continuously, is being given by a formula where you take the principal and you multiply it by e, the constant, raised to the RT. And R is your interest rate, expressed as a decimal, of course, and T is going to be your time. And the units of time will just about always be annual, because this rate will be given as an annual rate. So it might be 4% per year, and then T would be for some number of years. So essentially, you might say, well, how does this look like this function? Well, we've got what's called the initial value, A in the general template, but P here is how much you're going to start with. And that's going to make sense because if T is 0, or if X is 0 up here, anything raised to the 0 power gives you 1. So you would have A times 1, which of course is going to be A, or here you're going to have P times 1, which would be P. So your initial value is given by this term here. The interest rate, again, generally they're going to give you this amount of money, and the question's going to either be a question of how long is it going to take to achieve some new amount of money, or what interest is going to take to achieve some new amount of money. Either one of those things could then act as your variable. Sometimes they give you both R and T and just say, well, how much money you're going to have after a certain amount of time at this interest rate. You just plug everything in and it spits out the amount. So, we might have something like you're going to start with $500 and the interest rate is, let's say, 4% compounded continuously. And that's the thing you want to look for to use this formula. Continuously compounded for, let's say, 5 years, and find out how much money you're going to have. Well, you just say A equals 500 as your initial value, E to the 0.04, because that's 4% represented as a decimal, multiplied by 5, and then you would just go and put that into your calculator, and it's going to spit out a number. So I just did that on my TI, and I got 610.7013, so that would be rounded to $610.70 as your answer. That's a very, very straightforward way of approaching this. But maybe a more interesting question might be, how long would it take for that money to double, let's say? So now if you're going to start with $500, in order to double, you would have $1,000. And that would be 500 e to the 0.04 times some unknown amount of time. Now, the first thing you would want to do to make your life a whole lot easier is realize that you could take this equation and divide both sides by 500, and you would get 2 equals e to the 0.04 t. Now, there's two ways we could go about this. Essentially, this right side is saying, what's it going to take to turn this base into 2? What power do you need to raise e to turn it into the number 2? And it's easy to do that. We can find that out two ways. We could graph y equals 2 being this left side, and then graph e to the 0.04 t, which will intersect that red line somewhere, and that's going to be the amount of time it's going to take. So you get a graph that might look something like this, and come up here. This y-intercept there for the this side of the graph would be at 1, and you just have to find out where that intersection is going to occur. So you could just graph those two equations in y equals, put one in y1 and one in y2, and do second calc intersect and find the intersection point. It may have mentioned over the time in class that I think it with 6 or 7%, it's going to take somewhere in the neighborhood of 11, 12, 13 years to for that money to double. So at 4%, it's going to take even longer. So you'd have to set your window out here. I'd probably want to go shoot it out to at least 20 or something like that to see to be able to get a good picture of this. Okay, I just graphed those two on my TI, and it looks like that intersection occurs at this x value of 17.32868. So that would be, let's say 17.3 years until that money's going to double. Now, I did mention, of course, you could do it two ways. That graphing is one way. The other way to do it is you come back to your equation 2 equals e to the 0.04t. And you want to knock this e out of here. So what that's going to do, the way to do that is, so we take the ln of 2, and that's equal to the ln of e to the 0.04t. And the left side is going to be a number we're going to get off the calculator. And we get 0.693 for that. And now on the right side, ln is asking, what base do you have, what do you have to raise e to get this number? So it's saying, what power do you have to raise e to get to e to the 0.04t? And of course, that answer is going to be 0.04t. And so now we can just divide both sides by 0.04. And in doing so, you get exactly the same number that we got using the graphical method of 17.32868. So we just round that off, and it tells you it's got that much time. So that's obviously a much more efficient way. You don't have to worry about setting your window up or anything like that in your calculator, going into y equals and doing an intersection. And that's real valuable. So that's probably the most common use of an exponential function. Again, you could be asked for how much time it's going to take, as we were in that one, what the interest rate would be, which would be essentially the exact same process. It's just that you would have a t value, just wouldn't have an r value. And so you'd be solving for r down here, and that rate would be given as a percentage. The easiest way, of course, is if you're given the initial value, the r and the t, and just plug them all in and it spits out a number for you. One other type of exponential equation you might get is something like, you might have a common base of something like 5 to the x times 5 to the x minus 2 equals 13 or something like that. And of course, you're going to be asked to solve for x. Of course, you could try and guess and check your way through something like this, but what's going to happen here is the first thing you have to realize is that we're multiplying two things with like bases, and when you do that, you're going to add the exponents. For example, x to the second times x to the third equals x to the 2 plus 3, or x to the fifth. So adding these exponents together, we'd have 5 raised up to the 2x minus 2, because that's the sum of x and x minus 2. And if we have 5 to the 2x minus 2 equals 13, again, you could use the approach of graphing the left side and setting it equal to the right side to see where they intersect, or just take logs of both sides. Now, when we're learning about logs, we would think about taking the log base 5 of both sides because we want to isolate that exponent, but it doesn't matter. You can take log base anything of either side, but we'll take ln's of both sides. That's the most common base to use. So we're going to take the ln of 5 to the 2x minus 2 is equal to the ln of 13. Now, the right side of this equation, ln of 13 on my calculator, is 2.565, rounding to 3 decimal places. And the left side, you may say, well, why does using ln help us with a base of 5? ln was very convenient over here when we had a base of e, because the two actions just simply canceled each other out. Taking the ln of something and raising e to something, those two actions are inverses of one another. So it left us with 0.04t. Here, raising something, raising 5 to the something power and log base e-ing something, those are not inverse operations. However, we can use the power property for logs, which allows us to take this power and move it down in front and get 2x minus 2 times the ln of 5, and that's equal to 2.565. Now, that quantity ln of 5 is certainly something we can just get off the calculator. Right, I got that number off the calculator. It is 1.609. So we could just divide that off to the other side, and we'll have 2x minus 2 is equal to 2.565 over 1.609, and then we can add 2, and we get 2x is equal to that quantity, which is 3.594. 3.594, and now we just divide both sides by 2, and we get our solution of that number divided by 2, which is 1.797. And there we go. And that's about every kind of exponential equation you're going to get. It's, you know, a practical application here with the financial stuff, or just a straight up algebraic equation. Regardless of what's going on, though, you have to, the focus is get a single exponential equation equal to a constant, and then take ln's of both sides, use the power rule if you have to, and then isolate your variable. Pretty straightforward from there.